Hello. So in this video, I thought we would talk about the trigonometric values again, like sine or cosine or tangent. Maybe not tangent in this episode. Maybe not even cosine. But instead of using them how we usually do, in basically geometric relationships based on distance, what we're going to do instead is actually use them like a function, like we would normally do in various other maths. Less so in geometry, though we do occasionally, actually reasonably often. Up until this point, maybe less so. So we're going to be treating a trigonometric function, that's right, as our y. So we're going to have y is equal to f of x is equal to, let's say, sine. Let's try this out. And we're going to say that x is basically an angle in radians. We could call it theta. This could be a function of theta. Either way. But you just have to make sure you think of x as a angle in radians. So how can we start this off? First of all, I want to make a little table to simplify things a little bit. So this is going to be our x value. It's a bit cramped. It's going to be our function of x value. Now, where can we start? Let's start with x is equal to 0. That seems simple enough. X is equal to 0. So we're going to take the sine of 0, plug it into our function, and that's going to give us 0, as you're probably familiar with. It could be helpful to draw a little unit circle. I don't want to use too much of the space down here, but we could draw a little one. As long as we keep it small. A little unit circle. All right, the sine of 0 is just down here along here. And as you probably remember, you can judge sine and cosine based off of their coordinates in the unit circle. If you don't recall that, then you can just look back at the unit circle videos and come back when you're done. So let's mark that. The coordinates x is equal to 0, y is equal to 0, right? We know y is equal to f of x here. Now let's choose another x value. What's the next one we know? Well, the next one I can think of off the top of my head is pi over 6, which is 30 degrees, if you're thinking in degrees most of the time. And so that is going to be, again, if you've seen previous videos, you probably know this one. This is equal to 1/2. And now we'll graph that. I'm going to make some kind of bounds on our coordinates at 1 and -1, which will have an obvious purpose in a moment. And I'm going to make our bound on the x-axis 2 pi, just for the sake of graphing this. And we're going to mark out different important angles that we just know off the top of our heads are going to be useful. All right, so pi over 6, where's that going to be? It's going to be around here. Pi over 6, and we're going to have 1/2. All right, now what's the next one? Well, the next one I think of is pi over 4, which is 45 degrees. This is, of course, pi over 6, now 45 degrees. Now that is going to give us an interesting sine ratio of the square root of 2 over 2, or if you like radicals in the denominator, it's going to be 1 over the square root of 2, which is about 0.71. So I'm just going to put it a little bit above 1/2 here, not quite halfway to 1. And I'm going to place that really close to pi over 6. Not very different angles. And remember, we're only 1/4 through this length here. So that's going to be around here. Feel good about that. Now, that's pi over 4. Let's mark it in our little table, because our little table is almost as adorable as our little unit circle, but we don't need to dwell on that. Oh dear. Yeah. All right. So now what about pi over 2? That's a pretty obvious one. You probably know that to have a sine ratio of 1, that's 90 degrees. And so the sine, the y-coordinate along the circle is equal to 1. All right then, let's graph that. This is going to be a little bit closer. My drawing is not really benefiting the demonstration. So now let's keep going past 90 degrees. So the y, as you'll probably know, we can actually mirror things as we go past 90 degrees. So if we go another 45 degrees, we've essentially gone, oh dear. If we go another 45 degrees like this, because this is a 90-degree angle, it's complementary, so this is 45. And so we'll get the same sine ratio as if we went 45 only one time. So let's go another pi over 4. So we have 3 pi over 4, right? We're going 3/4 around the pi, which is 1/2 a rotation. And so that's actually going to get the same value, the same sine value. It's going to be around this 0.7 thing. And I should really scooch this over a little bit because it will actually mirror. Yeah, let's just get this as nice looking as possible, though it's hard to do. All right, I'm not going to bother with pi over 6 again, but what we can do is make the same argument. If so, we can actually just say that this mirror is going to be made, and if you don't believe me, you should check on unit circle, do the angle things. But we don't have very much time in this video, so I'm just going to put this out there, and you can prove it for yourself if you like. We're going to get this mirror value. And this is actually going to continue because the y-coordinates on both sides are going to be equal. All right. And if it helps to visualize, you can imagine that we're just flipping the unit circle on its side and starting at 0 again, right? That's essentially what we're doing as we add these new angles. But now let's go to pi. And what's pi? First of all, we haven't done the 3/4, but we already did that. So, and we've shown that it mirrors. So let's do pi. The sine of pi is equal to 0. All right. Probably know that one. If you don't, you can just look on the unit circle. It's going to give a y-coordinate of 0. All right. So now we kind of have 0 to pi, but I want to go all the way to pi over 2. I mean 2 pi. Oh dear. My voice is not assisting me. So I'm going to erase that so we have some more space. That's not really something important for the rest of this video. Now let's start going again. I'm not going to place in the pi over 6s like I said. That was really just to get an idea. But for now, the pi over 4s and pi halves will do. So we're adding another pi over 4. So we're going to get 5 pi over 4. Arithmetic, don't fail me now. And then we're going to go another pi over 4. And we're going to get 3 pi over 2. And then I'm just going to fill them in. 7 pi over 4. Just so we can have some ease when graphing these. And I might actually need to trim our unit circle down here. But we need it for one more second. So as we go below, you can imagine what we're doing is, I just like this, that you're flipping the unit circle on its side over and over again, and then going a certain angle again. So we're going to get these symmetries, but this time they're below the x-axis. So they're going to be negative values because they're negative y-coordinates. And if you still don't understand how that works together, then again, review the unit circle video. But we're going to have negative values. So they're essentially going to be the same magnitude as their components on the other side over here, but they're going to be negative. So how can we show that? Well, let's look on the unit circle. Let's go another pi over 4 down. So this, look at this. We're mirroring it. It's a mirrored image. Look, we can flip it around and look at it the same way. We have a 45-degree angle here, and so we're going to get the same value, but it's below the x-axis. And this will apply for all of them. So let's just graph them. Let's put a negative 1/2 here, and let's start graphing. I'm going to mess up the 5 pi over 4. now that you do get this is going to happen, I want to erase some of this so I can get some more space. We can leave the bottom half if you like, so we have kind of a unit semicircle. This is all we need right now. And now 3 pi over 2, that's essentially going another 90 degrees from pi, so we'll have the same as 1, but it's going to be negative. And then we're going to get the same mirroring effect, because now we're just passing the same thing on the bottom. If we flip the unit circle over, if we flip the semicircle over, we get the same values, but we have to remember that we're also flipping the x-axis. These values are below the x-axis, and hence their sine values are negative. This is just how the convention works, and it turns out it's used in a lot of more practical applications than pure mathematics, but it's also very useful in mathematics. We're going to have these negative values here from the unit circle having values below the x-axis in the case of sine, and on the other side of the y-axis in the case of cosine. So this is going to have the same pattern again, and we're going to get to 2 pi. We know the sine of 2 pi. That's just going around in a full rotation. It's equal to the sine of 0, which is 0. So we're going to get here. And look at this cool thing we found. Look at this kind of cool shape we've made. So when we were starting and got to pi, it looked a little bit like maybe a quadratic. Look how it looks like it's curving, and kind of its slope is accelerating downwards. If you're familiar with calculus, it's getting larger as we go on each side. And it's gradually getting slower and then eventually getting very negative. But in the case of physical analogies, I mean, never mind. But it's like an acceleration path. We have this curve that looks like a quadratic, and then down here we also have this curve that kind of independently looks like a quadratic, where we could say like, well, maybe something like that happens, you know, and maybe something like, you know, that happens. Oh dear, I don't know what happened to my pen there. That's not good. Go away. Go away. Go. No, not you. Come. No. Okay, we're gonna have to deal with that unless I bring in the eraser. Yeah, I think I'll do that. All right. So now we actually see that these two curves are connected, and if we try to approximate the curve by just kind of following it along and kind of guessing how it would take place, and if you actually use a graphing calculator or you graph a lot of values, it would become more obvious that the path of this curve is actually going to look something like this. It's going to come down like this. And this is pretty cool, because what does this look like? What does this look like? And we could go in the negative direction, you know, we'd have something like that. It continues into the negative. Remember that negative angles in trigonometry refer to angles where you're going around the unit circle in the clockwise direction rather than the counterclockwise, right? This is positive, and this is negative. You can think of it as subtracting angles. Usually you don't start going clockwise. Usually that's just how you subtract angles. But anyway. Now then, so this looks a lot like a wave. If you're familiar with something like ocean waves, it's kind of the clearest visual example. We have, what is this, a crest? And down here, a trough. I think I spelled that right. Looks good. And that's actually exactly what this is. The trigonometric functions themselves are used to model various what are called oscillatory phenomenon, where you have something like a wave with a repeating cycle. So that's what oscillatory is. Or you have a pendulum, or things that repeat in cycles. A lot of them can be predicted with trigonometric functions. which I think is very interesting. It turns out trigonometry has very powerful implications in physics, mainly, among many other things like mathematics, obviously. And, you know, if you look a little closer, a lot of those repeating phenomenon with waves actually contain triangles, and that's why they have this pattern. And so that feels maybe a lot more satisfying to prove that they're modeled by this, is that you can actually pull this out of the mathematics. But a lot of kind of wave-like repeating functions in nature follow trigonometric functions. And this is what is called, actually, kind of surprisingly, I don't know why they call this this a sine wave. I'm not sure what sine is supposed to be here when it's a sine function. That's mysterious to me. Or if you like the longer word, sinusoidal wave, which just refers to sine. Again, it's just kind of a fancier word, if you like that. But this is really interesting, and we're going to look at the implications of this and also cosine and tangent functions in the following videos. Thanks for watching.